Welcome, everybody, to another fantastic installment of the Planetary Science and Astrobiology Seminar. This week, we're very excited to have our own Dr. Annalisa Bracco from EAS. You may know her work from studying the Earth's oceans and climate, but you may not have known that she also is a big fan of atmospheric dynamics on other planets, and namely Jupiter. She's a not so closeted planetary scientist as well. So we're really excited to hear about the other part of her work today. So she'll be telling us about some really exciting stuff she's been doing with the Juno mission. So thanks so much, Annalisa, and take her away.
Thank you, and thank you for having me. I'm probably more known as a physical oceanographer, and my background is in fluid dynamics. So this is really where I'm going to focus the talk today. But I've been lucky enough to get trained in analyzing or trying to interpret some of the Juno mission data, especially the one from the JIRAM team. And I need to really thank Alberto Adriani and Alessandro Mura, who got me trained in those projects, and especially Alberto at the beginning, who are behind the JIRAM instrument as well. And it's been a lot of fun. It's been completely by chance. Before Brittany and I were talking about, she was mentioning her PhD advisor. Yeah, my PhD advisor was also a great guy, but peculiar. So I went to work. I had my sabbatical in Italy, and in his institute. He's the director of the institute right now. I barely saw him, but I had to complete some stuff and work with a student there the following year. So I went for a few weeks, and I didn't see him at all over all this few weeks period. And he told me, well, we should really talk science. So why don't we go together to Rome? Because I have those 2 meetings, and you can just tag along, and at least we get the chance to talk. And so we did. Except that then he told me, well, you're going to this meeting about Jupiter tomorrow alone because I'm not really interested and I have no time. So just go, introduce yourself, and help them out. And that's how I got involved in this. There's been a lot of fun. So what do we have at this point is 4 years of data. The Jupiter poles, these cyclones, sorry, I do come from the oceanography community, so I may be calling them eddies during my talk. It's what we use for vortices, and there can be both signs. But what we discovered in 2017 is that the poles of Jupiter's, both the South Pole and the North Pole, have a bunch of cyclones which have size between 4,000 and 4,600 kilometers. They're all very similar in size. And you have 7 plus a central one in the north, and 5 plus a sixth one in the south. Actually, sorry, you have 8 plus 1 and 5 plus 1. We don't know why. Those are the preferred shape that those cyclones have organized. And what we have at this point is 4 years of observation provided by JIRAM. JIRAM detects the infrared radiance and in the wavelengths between 4.5 and 5 microns. And does that with a resolution which is between 15 and 60 kilometers. And has been seeing the South Pole completely much more often than the North Pole. So we have over 30 flyby of the South Pole, and we have less than half and not complete of the North Pole. The perigee approximately is 4,000 kilometers above cloud tops for Juno, and what I'm going to discuss are really the JIRAM, so the Jupiter InfraRed Auroral Mapper imager, and the JunoCam. So I will also show 1 or 2 images taken from the visible camera. It's a very interesting amount of data, and the interesting part is why we have those structures. So why do we see those very large cyclones? What are their characteristics? What is their depth? And are they stable? Are they there all the time? I mean, we know Jupiter of the red spot, but and has been there for a long time. What do we know about those cyclones is, of course, much more recent, and came really like a surprise. At the time, we really had no expectation to see structures like that, and we had even less expectation to see structures that were stable at those latitudes. So looking at the data, what can we say? Well, stability, surprisingly, is very strong. They are very, very stable. We have now 4 years, as I said. Again, the South Pole is much better sampled than the North one, but for everything we see, there have been no changes in shape or no changes in number through those years. There was one episode of an intrusion in late 2019. So there was a new cyclone that entered in the pentagonal structures in the South Pole and formed an hexagon. But it's been destroyed. It didn't last very much. It lasted only a few months. And the best we can say is that it did not merge with the pre-existing structures. And this is the sequence that tells us that. So those are images from July, November, and February 2019, and then 2020. This is the first indication. In July, you have a first indication where the arrow points of a formation of a new cyclone, and you also have an opening between two of the cyclones in the formation at the South Pole. The cyclone, the new one, which is the order, as a diameter of the order of 25 to 3,000 kilometers, push in, but by February it's gone, and there is no trace of it. It's not merged. We don't think that this black spot that we see here, it's a remnant of this cyclone, because it's actually counter-rotating, and also this one didn't last. And it's kind of common to see small anticyclones getting close and getting destroyed, the large cyclones. So, kind of a mystery. It kind of disappeared without leaving trace. There is no really evidence for merging. From a dynamical perspective, the fact that you have a lot of cyclonic vorticity near the pole is justified by the Coriolis force. You would expect to have more cyclonic vorticity going towards the pole. You also expect that if you have cyclonic vorticity equatorward from the poles, that cyclonic vorticity, just by the beta plane and the presence of F, will move towards the pole. So this is essentially what this intruder did, was a cyclones outside the 80 degrees latitude that moved through towards the pole, and that probably found the right time when there was space for him to get between the other two cyclones, but then was gone. Again, we have 4 years, and we can now manage to figure it out what is the rotation speed of the structures. The whole structure rotates really, really slowly. It's about 1 order of centimeter per second, and we do have wind speeds there that are at least of the order of the meter per second. Most likely are of the order of the 10 meter per second. They rotate really slowly and with more or less constant the whole structure, so that each cyclone it's moving with approximately a speed of 7.5 degrees per year. So it would take about 50 years to complete a full rotation on itself of the whole structure. And in the North Pole, the velocity is about half of that. We do have larger uncertainties linked to having only two flyby on the cyclone indicated as number 7 and number 8. And those two are really the ones that cause most of the uncertainty. So what it looks like is that the northern pole, all structure is moving with a speed of about half. And so it's going to take hundreds of years for that to actually go around itself. At the same time, each cyclone rotates around his center very, very quickly. So it's very fast around itself. There is a rotation period of just a few days. But the whole structure is really slow at going around. So those are important characteristics, because if you want to try to understand how deep they extend, you need to explain them. Then we can take a closer look at some of them, and this is one of the CAM images, and what you see as far as Jupiter goes is a zoom on one of those cyclones, and you just see a piece of it. What you see at the bottom is the actual image. What you see in the middle, it's a series of wave structures that have been identified and removed with a filter, and the top is the filtered image. What you see on the other side is an image from the Southern Ocean of 3 cyclones. There is a fourth one too, but it's covered by clouds. And the reason I put it there is to show that there are some similarities. There are some strong similarities. What you see in the Southern Ocean is actually a color, a modified color image, which is indication of primary productivity. Where you see more green and yellow, it's a large concentration of chlorophyll. Where you see more blue is lower concentration of chlorophyll. Those are all cyclonic eddies as well. Same reason, rotation of the planet. When you get close to the poles, you tend to converge all the cyclonic vorticity. But the reason to show that is really to look at the structure of the eddy per se and all the characteristic, the gradient that they have around, the fact that you have the formation of these little eddies on the side. All this kind of instability is very much reminiscent of what we call submesoscale instabilities in the ocean that we have been studying for the last 20 years or so, and that are very, very peculiar. You don't find them in the atmosphere. You find them where you have a well-mixed top layer, so near the top, with a boundary at the top. So it's the upper part of the ocean. It's most likely the bottom, but it's the bottom turbulent boundary layer of your fluid. So what this is suggesting of is really the presence of the same kind of instability processes. Even more interesting, if you analyze the wave field, what you see, it's very similar to what you will see in the ocean in presence of Langmuir circulations. And so, it's the interaction between the Langmuir cells, which are wind-driven, and the submesoscale turbulence. So you can get also an image which would include the wave field in the ocean if you take a model. We don't have observations at that resolution because the Langmuir cells in the oceans are order of 100 meters. But if you take a rich submesoscale eddy field with submesoscale instability in the ocean and you add winds and you simulate that in a model, you do get also wave that are very similar to what you see on Jupiter. So this is really how I got entrained this project to me when I saw some of the images, and I actually saw them the first time in kind of bluish colors, which is kind of the same palette that my background. That to me was ocean. I could not even think that that was something else at the beginning. This is another image, which is a zoom on one of the eddies that we have on Jupiter, one of the cyclones. Sorry, should not call them eddies. And what you also see is the presence of those spiraling arms, the presence of those instabilities at the borders, and of these other small eddies at the center. Again, vortices. And here it's a simulation in the North Atlantic. This is near the Gulf Stream for a large cyclonic vortex as well. In a condition, it would probably be even closer in resemblance had we had a simulation for winter. This is a simulation for spring, and so the mixed layer is a little bit shallower. But really, there is a very strong resemblance, and if you have worked on ocean simulations and oceans at mesoscale for a while, what you see in Jupiter images is the same kind of instabilities. I see them in the Gulf of Mexico. The presence of those small eddies inside the large vortex, it's really characteristic of that. And you don't really get it with other systems of equations. So what really happens in the ocean is that we have motions that are like two-dimensional, or that are mostly two-dimensional. So you have, if you consider planetary or mesoscales in the ocean, which means that if you get down to scales of about 50 kilometers, rotation of the planet and the geostrophic balance dominate. And so you have non-local dynamics, and your energy spectra resemble those of 2D turbulence. But if you start looking a little bit more in detail, and you can get to lower spatial scales, and you can include what happened, especially at the vertical boundaries, down to kilometer, then you start seeing local dynamics. And when the distinction between local and non-local is quite important, because it refers also to the range of interactions that the velocity field exerted by those cyclones will have. And in terms of energy, you see shallower spectra, which go like -2 or -5/3 instead of being with a -3 slope. And you find all those instabilities that emerge that have then an outcome as the one that we see on Jupiter and the one that we see at the ocean surface. So everything I see just qualitatively, it's indicating that Jupiter must have at the poles a relatively deep but well-mixed surface atmospheric layer. The easiest way you can simulate the instabilities that we see at the ocean surface is through what is called surface quasi-geostrophic approximation. This is two-dimensional, but simulates really well the spectral properties and the instability properties of the ocean surface. Of course, it's not sufficient. You are essentially just simulating the upper layer, assuming that everything in the vertical is constant. But has the same properties in terms of locality. So this is a simulation that I run this pretty much over the weekends, and you can see again, and I used in this case a palette that was a little bit closer to the JIRAM images. And what you can see is a cyclone, and what you can see is all these little instabilities and structures that resemble very much what we observe. Really, those vortices that form at the boundary, the spiraling arms, very, very similar. What I did here was also to add a beta plane that was relevant to Jupiter. What I can say from the beginning is that I get very nice cyclones that goes towards the pole. If I have the right beta approximation, they merge, and you get a big one at the end. You don't get the structures that you observed. Those structures, however, if I put it in as initial condition, and I'm careful to keep a range of distances between each vortex, then I managed to keep it pretty stable. However, it's not explaining how the system formed, right? I mean, it's just saying that if I have it, I can explain why it would stay there for a long time, but it's not explaining why I would emerge, because that my model is unable to do that. As I mentioned, what separates the submesoscale turbulence kind of regime from other that are just called geostrophic, and so where really Coriolis is the main balancing power, is the energy spectra. So what we can do is that we can compare the power spectra from the JIRAM images to the one that we have in the ocean. The problem is that the submesoscale instabilities that we get in the oceans are also generating small convective motions within the mixed layer, essentially. And that means that the spectra is not discerning or is identical to the one of convective plumes. So we are not going to be able to separate between a pure convective plume from Rayleigh-Bénard convection, for example, and something that instead has a density component in it, and that is stably stratified, which is what I think we are seeing in the Jupiter images. What we did was to take this beautiful simulation from the ocean and really select two cyclonic vortices. One is larger, one is smaller, but it doesn't really matter. And we also took simulations of convection and convective plumes, and those are direct simulation of Rayleigh-Bénard convection with a parameter range that could be relevant to Jupiter. And we have the convective plumes, so these are direct numerical simulation of convection. We have during convection, and we also consider once convection stop and things relax a little bit. Obviously, it's immediate to see that the field that we get both during convection and after convection are quite different from the one that we see in Jupiter images, the poles. So this is, again, one of the image. This is the South Pole, seen just in a different color palette. And what we are also considering is a transect that goes north-south across two of the cyclones and also just in the middle one. So this is what we get in terms of just cross-section. So this is just to compare the variance and the kind of variability we get. At the top are the ocean eddies, then we have the Jupiter cyclone, and at the bottom we have the convective plume during active convection and after convection has stopped and there is a relaxation time. There is a very different variance, and I'm sorry, I just realized I never put down the variance for the Jupiter cyclone. The Jupiter cyclone has a variance of around 0.5. Unfortunately, I didn't write it down. Convective plumes have a variance that varies between 103 or nearly 0. Notice the very different axes on the two. In the convective plume case, so when the convection stops, the plume relaxes really quickly, so the variability that you see is actually very, very small in amplitude. And the ocean eddies rescale to the Jupiter range are very, very close. So that's an indication that, a small indication that we may be indeed seeing something that is much closer to the upper ocean than to just pure convection. I also look at spectra, of course, and I ran a bunch of simulations using an ocean model, which is ROMS, using the surface quasi-geostrophic approximation, and focusing just on the eddies or eddies plus background, it doesn't really change in terms of spectra. Those are compensated spectra, which, well, the top, it's the spectra as it is, and then the bottom two figures are compensated. And I'm showing the minus 5/3 slope. So I'm dividing the spectra by by k to the minus 5/3 and the minus 2 at the bottom. It's clearly not a minus 3 because the compensated spectra are pretty flat with minus 2. And it's definitely the case that the minus 2 seems to work better both for the eddies in the ocean and for Jupiter. As I said, convection is minus 5/3. The upper ocean, there are still debates, and you can get both at least in the observation. It's very hard to distinguish and to really put an error bar between a minus 5/3 and a minus 2 are very similar numbers, and usually your error bars on spectra brings you both out. I did try, there are some, here I've looked through a bunch of images and I've used them all the one that I have, all the flybys that I had available, and there are some flybys where it's a perfect 5/3, and there are some flybys where minus 2 works better, which that's to be expected. So again, we seem to be in the right direction. I don't think we can distinguish between different theories or different generation mechanisms. So what are the implications at this point? Everything seems to suggest, especially, I mean, putting together the variance and the spectra result, that there is a well-mixed surface layer at in the atmosphere. What we have done so far does not discriminate about the origin of the eddies. So, and again, I should use cyclones. They can be deep or they can be shallow. And when we mean deep and shallow here, it means few tens of bars into the Jovian atmosphere for shallow and tens of thousands of bars for deep. If they are deep, then it's reasonable to think they are convective plumes, and it's reasonable to think that they are convective plumes that then have a signature into the well-mixed layer at the top. And so what you are observing is the mixed layer, but the stability of those cyclones come from having a convective core underneath what we observed. Obviously, so I did not have any funding. I could do in my weekends surface quasi-geostrophic simulations because they're relatively quick, and I can obviously do ocean simulation or use what I have. But people have run and rushed in trying to simulate the stability and the structures. Those two papers were published in the Journal of Fluid Mechanics by a group in Cambridge, Renaud and Richel. In England, it's actually not necessary. One is in Cambridge, the other is not. Anyway, they use a quasi-geostrophic model. Quasi-geostrophic model, it's a zero-order approximation close to surface quasi-geostrophy, but without the possibility to, it's a non-local approximation. So your spectra are going to be -3, etc. And all your interactions are going to be like that. They use a toroidal vortex, and then they put an instability, and if the instability has the right wave number, obviously it's going to generate vortices of the same sign. Not very surprising. You just put the instability in the way you want it. The interesting result here is that if the vortices of the same sign are accompanied by a vortex of the same sign in the center, then there are good chances that your structure will be stable for many M's, for many number of vortices. All this work has no beta and has a fixed latitude. I can tell you that my surface quasi-geostrophic model did the same. It was absolutely perfectly stable. The problem is that the moment I put beta, everything merged into one. So not very useful, except for the instability work, which I decided was not very interesting, and so I never published from my simulations, because there are theories behind that tell you that that those structures can be stable based on point vortices, so something really mathematical. But again, what you also see here is that those cyclones or vortices to be stable need to be separated by some distance, and that's really the tricky part. You have to find the right one. Again, there are no observations of the wind field, which is observed but not very well, but there is no indication that the forcing field at the surface atmosphere has a preferred wave number. Then there was a paper that came out in 2020 by Lee et al. This is the Ingersoll group, which is involved in the JIRAM observations and the Juno observation. And what they did was to use a shallow water model. The shallow water, it's a higher order approximation that can include both the surface quasi-geostrophy and the geostrophic one. But you are assuming that your cyclones are shallow. They, however, put it on a sphere and they put it on the pole. So they have beta. So this was a big advantage or a big step forward. What they find is that you can put those cyclones outside the 80 parallel, and so equatorward, and they will move towards the pole as they should. And they do it with 5, and they show that at least with that configuration, 5 plus 1, if one is closer and can get to the center first, the other ones can get into a stable configuration if they are of the right depth, they are not too thin or they are not too deep, and most importantly, they must be shielded by an anticyclonic vorticity around them. So what they really do is to put them in the initial conditions with those characteristics. So they put them shielded. It's very hard from the JIRAM images to see if there is around each of those cyclones an anticyclonic frame, because it's probably below the resolution of the instrument, which is at the end of the order of 60 kilometers for most of the time. But from the JunoCam images, we don't seem to have any indication of a clear cut shielding of opposite sign around those cyclones. Again, the JunoCam are few and usually don't cover the whole cyclones. The other thing that they did was to add a cyclone from the outside, trying to reproduce the 2019 event. What they see is that the cyclone can move in and can eventually do exactly what was observed. So 2 will move apart, 2 of the existing will move apart a little bit, and the new one gets in the middle. And so you get to a new stable situation. They run it for a very long time, and the 6th one doesn't move out. So the problem here is that what instead we observe is that the 6th one entered, but then disappeared in 2 months. And that is really fast. The other problem of this model that they show in box, but they did not put in the paper, unfortunately, is that the overall structure, considering realistic winds, at least in terms of magnitude, rotates really, really fast. Like rotates multiple turnarounds in a Jovian year correspondent, which is really not what is observed. It's moving by 7.5 degrees at most. So those are problems that still exist with this model, and are problems that we know now better that they exist with this model because we have the 4 years of data. When they did the simulation and published the paper, the analysis was pretty much stopped at early end of 2019, and so they didn't even know that, for example, the new cyclone disappeared. This is a fantastic work that has been done instead with a laboratory experiment. So you can get And this has been done, it's been published very recently, and has been done kind of independently. They kind of realized at the end that what they were doing could have been relevant for Jupiter. And this is done in a lab. It's a tank, and you reproduce the configuration that you see, for example, in the North Pole. You get the cyclones. You don't need the rim around each of the eddies to get the stability. You need the center. Here, the center is a cylinder, but you can imagine that if you had a deep cyclone there, that would be enough. The problem is that what you need to generate those instabilities and the eddies, which are generated from zero background. I mean, there's just, you put the fluid at rest, you start the motor, and you add a wave. So something very realistic that could have happened on Jupiter, no problem. Only issue here is that you need a bathymetry. And you need a very specific bathymetry. And there is no reason to think that we do have a conical mountain at the bottom of Jupiter poles. Even if there is some possibility that we may have some kind of equator versus pole difference, and so that something may have accumulated at the pole in a different way. But this is a beautiful experiment. They realized it only at the end that there was possibly some relevance for Jupiter. The real issue, it's trying to imagine that we have a configuration that is like that. This also points to deep, potentially relatively deep cyclones, but you don't need convection. This system does not need convection to generate those structures. Then there are the deep convective models. The leader, I would say, in the field of simulating deep convective atmospheres in Saturn or Jupiter, gas giants anyway, and they do both simulations and lab experiments. It's Jonathan Arnoux at UCLA, and if students are listening to this talk and you manage to get to UCLA, he's a very nice person, and he will give you a tour of his lab, and it's a lot of fun. I've done it when I was there the last time. I really had fun. So send him an email, drop him an email, and ask him, because it's really worth seeing what they do. Garcia et al. In 2020 used essentially the model that Arnoux and his group has developed, which integrates the Boussinesq thermal convective equations, and they try to explain the existence of a single vortex on Saturn and multiple vortex on Jupiter using this model, and the results is what you see in the image. And even with a lot of imagination, I mean, I can see that the model 1, which should be Saturn, it's closer to have one structure, and that model 2 is close to have a mass, but I cannot see what we actually observe. So for me, it's very hard to link directly what those simulations are doing and what we actually see on Saturn and Jupiter. The problem with those simulations is that are global, are on a sphere, are computational, extremely intensive. You can get to a Rayleigh number, which is essentially a measure of how far you are from laminar conditions, and to a resolution that are limited. So it's going in the right direction. I don't think it's really a satisfactory explanation of what we see. Then there is another approximation that has been used for the first time in planetary context in 1999, and that is the anelastic approximation. We are again in deep models and deep convection. This one was proposed in 1972, and essentially what you do in order to save computer time and make your calculation easier is that you filter out sound waves. You don't necessarily assume hydrostatic balance, but you remove the sound waves from your equations. You get into two troubles. So Boussinesq does not conserve mass. So you have already that. And, a system that does not conserve mass has its own issues. But when you do also the inelastic approximation, you also leak energy. So you don't conserve mass and you don't conserve energy. So as you can imagine, as got some complaints from a number of people saying that it's a little bit hard to imagine using it and getting something that makes physical sense. However, because it suppresses the acoustic modes, allows for a larger time step, and so you can develop the turbulence much better, and you can also do a better job at simulating the right Rayleigh number. So Yadam and Bloxham used it, and they applied it specifically to Saturn, and they published in PNAS last year. And this is what they get for Saturn, and this is a it's a 0.05 below the surface. So this is a typo in my presentation. So the video is showing what Saturn pole will look like at 0.95 radii, so 0.05 below the surface. And when you actually look at the surface, they do have images for that. You don't see the structures, but you actually get the imprinting of just the central cyclone. The very nice thing about this is that in terms of Saturn, it's almost able to reproduce the rotation rate, which is also very slow on Saturn. What they show is that they actually reproduce it by, it's still too fast by a factor of 3, but we are talking a factor of 3, not a factor of 300 like the shallow water did. What they also show is that there is a dependence on the Rayleigh and the Rossby numbers, which are connected, of the fluid that they are simulating. So if they could go a higher resolution and have a higher Rossby number, the drift will slow down. They show that that's what they get, but they are still far from getting the right one. They just show the tendency by doing a short run at a slightly higher Rayleigh number and showing that indeed the rotation of the whole pattern slows down. All this is, to conclude and say that what we know at this point for Jupiter is that the polar cyclones are long and are stable, and that they rotate really, really slowly, fast only around its center. The overall rotation is about 1/100th of the zonal wind, and is also at least 50 times smaller than the velocity at which the smaller vortices that are equatorward of 80 move with. So the only model that we have at this point, explanation that we have at this point that justify those rotation speed for the whole structure is that it's a deep convective plume. Only other possibility is that we do have a bathymetry and kind of a accumulation, pretty substantial accumulation of material near the pole. So the best I can think of is that we have a density stratified convective flow with an upper well-mixed layer near the surface, where on top of the convective plume, you also have conversion of variable potential energy into kinetic energy via baroclinic instability as it happens at the ocean surface. The other interesting part is that the rotation speed at the North Pole, it's about twice as slow as the South Pole. So it takes 100 years to complete a rotation on the North and 50 years for the South. And how do you justify this? One possibility is that those convective plume have a different depth, but to me, what seems much more likely is that there is a density difference in the polar atmosphere. And so I'm really pushing my co-authors right now to go into, look into that and try to see if we can. There is a little bit of elemental analysis that can be done. Unfortunately, what you really see from JIRAM are the clouds, and so not a lot. And the eddies are very thick clouds on top of them. So you can do a little bit of analysis of what is outside the cyclones, but I'm trying to see if we can figure it out, differences in terms of heavy elements between the north and the south that would justify some of the observations in terms of rotation. It may be possible, maybe not. But that's, to me, is the most interesting next step. And if you're interested to know more, the first paper in Nature by Alberto is definitely a great reference. And then we published in JGR Planets last year. And we are in the process of submitting a new manuscript probably next week. And with that, I will stop sharing and take questions. And thank you very much for your time.